Right. We are now recording this lecture. So is there anyone who is facing issues? Please raise your hand. Vishal will come and help you. Okay, he'll also just make sure that if the necessary software is installed on your machine. Has anybody been able to check if Jupyter Notebook is installed on your machines? Is it there? Not there. Okay. Please check Spider. SPYDER. The BTech students would know. You would have used it in your first year labs. Is it there?
Yes, sir.
Okay, so that should give you the necessary environment to run Python codes. So for today, what we'll do is you can use Spider. From the next time, we'll make sure that virtual machines are installed on your machine on these computers, so you can run them. Whatever works for you. In the end, we need to run a couple of Python codes. That's all. How many people have never used Python before today's class here? Can we see a raise of hands? So just 3. Okay. So then these 3 can seek help from Vishal. He'll help you, or you can seek help from the people around you. So we'll start with the lab for today. So step 1 was to have a virtual machine. Although we don't have time for that today, so what I'll do is I'll quickly run through the steps, because if you want to run some software, you don't need to keep installing it every time on your machines. You can use something called a virtual machine. So this is like a complete operating system, but inside a file. So all you need to do is you need to have a software called VirtualBox, which will then allow you to run a virtual machine file. So virtual machine files typically are large, starting north of 5 gigabytes or 6 gigabytes, but they'll have a complete operating system. So I have a Windows machine that I'm running, but that will allow me to run as many Linux systems I want over it. And the other thing is you can make a machine and you can share that file. So that is what we do typically in a class. We'll share the file with all of you. You can run that file and it'll have exactly the same image. You don't need to install anything depending on your hardware. So here we have already made a virtual machine available. So you might have seen a message from Vishal on the Google Spaces that there's a link for a virtual machine. So you can even use that for your own laptops and desktops. Okay, so let's, I'll share these slides with you. There's a password, etc. available here. The next step was to create a virtual environment. Again, this is required if you want to install some software. So in Python, typically you have different libraries available. So if you install that on the base operating system, what can happen is that your Python can stop working, or it may not be compatible if you update libraries and so on. So it's always safe to create a virtual environment. That is, an environment is inside a virtual machine. So virtual environment means that this allows you to have multiple copies of or different copies of different versions of Python, for example, or different versions of libraries in Python, because every few days you'll see a new library, a new version is released. Sometimes we don't want that to affect our base OS. Okay, so it's always good to work in an environment so that you can delete the environment once you are done, or you can share the environment details with someone else as well. So this was to install Jupyter Notebook. Again, Jupyter Notebook is a framework that allows you to run Python codes inside one single file. So you can have multiple Python codes in one file. You can also have markdown, so you can have some, for example, questions for the labs and so on, and then answers can be there as codes. So it allows you to encapsulate all the information, including problems and answers and everything, images and all, in one single notebook, rather than having a text compiler for something, a PowerPoint slide for something, a separate handout for problems and so on. So this is a nice environment, and we'll be using this because we'll have multiple problems per lab. The last step was to download and open the IPython notebook. This I have not shared with you today. If I share the notebook with you, then you'll have the solution, access to solution. And I don't want that before the lab, so that you try to practice the problems yourself. But after the lab, I'll share the Python notebook with you so that you can use it to run codes if you want. Okay, so this was a quick summary. So let's jump into looking at the codes. So have you been able to access Moodle? Anyone facing issues with running Moodle? Okay. So please download Lab1 and have a look at it. So you should be able to see on Moodle under Discretisations, there should be something called Lab1 questions. So clicking that will give you access to the problems for Lab1. So let's start with problem 1. Now again, strongly recommended from next time, please practice the problems if you get a chance. So the first problem is, let's look at the learning outcomes. So this is introduction to Python. This is just introducing you to how to use Python. A recap for many of you, something new for a couple of you as well. So this exercise 1 learning outcome is to be able to understand what are modules and how to import them. Learn about numpy module, which is helpful when doing numerical calculations. Learning about loops, particularly for loops, and a couple of other things as well in Python. So the problem says that you have to calculate the square root of 2 using the Newton-Raphson method. Now, Newton-Raphson method, if you don't recall, it's basically an iterative method to calculate the solution or calculate the root of a function. You don't need to recall the details of how it works. I've given you an iterative formula. So it says that you can start with an initial guess for the square root Sn. Let's say you start with some value. I mean, you don't know the value, of course. So let's say you start with some guess, and x is here the number that for which you're calculating the square root. So x would be square root of x should be 2. Okay, and then you can calculate the next guess using Sn plus 1. So it's simply an average of Sn and x by Sn. And then if you keep doing that through a loop, that will the solution Sn plus 1, or the sum of the the sequence in this case should converge. The sequence Sn should converge to the square root of 2. Okay, it's a very straightforward code to work with. So for this to write the code, you will need an editor. You can use Spider. So in my case, I have the virtual machine available with me, so I will run it. For you, you can open Spider. So Spider is SPYDER. So this is how a virtual machine would look. You simply would click start, and it will power up after a few minutes. So you can see that it actually looks very similar to having an actual OS on your machine. So this is now a Linux OS that I am running. So as I said that I would want to have a virtual environment. So I am enabling a virtual environment, and then I will be able to run the code. So if you want to launch Jupyter notebook, you have to write Jupyter with a py, okay, and Jupyter -notebook, and you press enter, and that will start running the Jupyter notebook server on your machine, and then also allow you to also opens a web page which basically is running the notebook. So this is how a notebook would look. It's an IPYNB extension. Okay, so we simply would click it, and that should open the notebook for us. Just a second, I need to check something. So I actually opened the wrong virtual machine. So I can have multiple virtual machines. So I noticed that the Jupyter notebook version I opened was an old one. So typically if I create a notebook in a newer version, that the forward compatibility may not be there. So if I have created a notebook in a newer version, your old version may not open it. So it's better to have the latest version. So this so this time hopefully I have the so this is version 702 and that is what I wanted. So those at the very back, can you still read the screen? Is the font okay? Okay. So in a typical Jupyter notebook, what you will see is you will have a markdown cell which has the question given, and then below that we'll have a cell where you can have the code. So just to go a bit quick, in certain situations what I'll do is I will rather than writing the code, I will discuss the code with you, and then I will also share the code over Moodle so you can download and run it by yourself. Actually, let me share it on Moodle as well, just to make things easier for you. Or let's share it on Google Drive. Solutions we'll share on Google Drive. So if you go to announcements on Moodle, you'll see a link to Google Drive link for books and codes. So if you click here, the Google Drive link is available. Just click that, and that should take you to the Google Drive link where you can download the code from. So I'll upload the code there. So for those who have Jupyter Notebook, you can use the pynb notebook file, or an HTML file is also given, which is basically a hypertext markup language having all the code and everything in it. So it's a replica of the Python notebook, how it looks, but it's not a Python notebook. So you can simply open the HTML file from the Google Drive link, and then you can copy the code from there into Spider. Now, if anybody is facing any issues, please feel free to raise your hands. This is a lab / tutorial, so we want you to be able to understand. It's independent of lectures, so please feel free to ask. Right, so let's look at the solution. So here what we have is, the first step is to import numpy. So numpy is a numerical Python module that allows access to many numerical libraries. So we'll import that because the square root function sqrt, which is used to calculate the exact square root, well, exact in the sense of the one that's available in Python. So that function is made available. Now I'm assuming that you have used at least one programming language or MATLAB before coming to this lab. So you should be able to understand this idea of having functions and modules and so on. So once we import the square root of 2, let's look at the line numbers. So in line number 1, then line number 2, we simply initialize the value of x equal to 2.0. Now I could change x, but in this case I want to calculate the square root of 2. So I'll make x equal to 2. Line 3 is to calculate the exact square root of 2. Because when I do it using a numerical technique, iterative technique here, I would want to calculate or estimate how correct my estimation is. So for that, you need an exact solution. So this square root function will give you an exact solution stored in y1 that you can use to compare the correctness of your solution. So line number 4 simply prints y1. Line 5 is to give the maximum or the number of iterates. So 500 iterations is what we will use to estimate this sequence. So we'll run this sequence 500 times. Okay, so s n plus 1, so n in this case is 500. So we'll have a total of 500 iterations run to get the solution or to calculate the estimation. Okay, then we have a loop. Sorry, then we have s. So you have to start with an initial guess. Because remember, Sn plus 1 is a function of Sn. So you have to start with some Sn. Some S naught is something that you have to start with. So in this case, we start with 1.0. I don't know the solution, so let's start with 1.0. Line number 7 is 7 and 8 are loops. So you start the loop from I in range k. So range function will return a list of numbers starting from 0 all the way to k minus 1. So this basically allows you to run a loop k number of times. That's pretty much it. Okay, and then we have the iteration formula in line number 8. So we say s equals half of the average of s and x by s. So we don't have n plus 1 and n here. What we do is we calculate the right hand side for a given value of s, and then we assign that into s only. So basically we update the value of s. Rather than having two separate variables, we store only one latest value of s and keep updating that, because once we have an updated value, we'll not need to access an older value. So we simply say s equals an average of s and x by s. In Python, indentation is basically telling us that this part of the code is under the for loop. We don't need to explicitly define blocks in Python. We can have indentation, and then we put the value of s into y2 once the loop. So you can see that line number 9 again is starting from the first column in the code. So that's outside the for loop now. And then we print the value of y2 and the difference of y1 and y2, which is simply the error. Right? And in Jupyter Notebook, if you want to run something, there's a play button on the top, or you can simply use Shift Enter as the shortcut for this. So let's just run it. So if I click the play button, you will see that below the code cell, the output also gets printed. So we have the value of y1, which is the exact square root of 2 calculated using numpy. y2 is the one that we have calculated, and the error is printed below that. So in this case, the error is of the order of 10 to the minus 16, extremely small. And then we can play around with the value of k. So let's say I only want to run 10 iterations. So I just change the value of k and run play again, or run again. And again, even this time we see that the error is quite small. Let's make k equal to 2 and then see. So if k is 2, then the error is of the order of 10 to the minus 3, but it drops quite quickly. So even at k equal to 5, you get an error which is extremely small, only in 5 iterations. And if you're motivated enough, you can actually print the value of error as a function of k. So after every k, you can print the value of x and see how fast it is falling. So that you will be able to do once you know how to plot things, which are further problems in this lab. So what I'll let you do now is I'll let you work on your own pace. So what that means is the solution has been made available to you for the different problems. Please read the problem, read the solution and run it. For a couple of key exercises, after a few minutes, I will do them again in front of you. Otherwise, you can try things by yourself. That's the best way to work. If you have any questions, please raise your hand. Vishal or myself will help you. Any questions? So the next few exercises, exercise 2 will help you understand the idea of lists and arrays. So the main difference between lists and arrays is that in list you can store or you can combine elements of any types together. But arrays typically, will only allow you to have elements of the same type. Okay, so lists are usually avoided when working with numerical numerical works. So in this kind of codes where you want to work with large data structures, all of which are storing data of the same type, then you should work with arrays, which is what you want. Okay, so these exercises will allow you to understand the difference between them. So please try running these codes and understand the ideas. Right, so let's have a look at quickly look at the idea, the difference between lists and arrays. So if I look at this code cell that's highlighted, so what you can see is that W is a list here. So W will hold a collection of items of different type. It can hold. So for example, this word hi with single quotes, it's a string. And then the second element, Z, was another element which was defined in the cell above. And then the third one is actually a list which contains 2 items. Okay, so they are all separated by commas. So if you run, if I run this code cell, well, I need to run the one before the hand so that Z is defined. So Z is now a collection of 1, 2.0 and hello. And see that 1 is an integer and 2 is a float or a real number. It has 2.0. So they are different in programming language. Okay, a floating point number, which is a real number, and an integer, they are different types. Okay, so now if I run this code cell, now we can see that W, which is a list which has a string in it, it has another list which contains data types, structures, elements of different types, and then it has a third list. So it has 2 lists and 1 string. So this is the idea of list. A list can have as many different types of elements as you want. But arrays, on the other hand, if we look at the arrays here, for example, in this code cell, let's run it. So what we see is that we are importing numpy as np. Np is just a short for numpy in this case. And then we use the np.array. So array is a function available in numpy which allows you to convert a list into an array. And that is typically how we work with, how we generate arrays in Python. So you start with a list and you can convert that to an array. So once you convert a list to an array, then this array will have elements of the same type. Even if I define them, differently. So let's say I make, instead of saying a 2 point, which means a real number, I make it 2. So that's an integer and a real number in the list. But when I run it, we'll see that they'll both be of the same type. So it will automatically convert, the array function will convert an integer to a real number to ensure that you have the most general type available in the array that you get towards the end. And what we are doing here is we are simply multiplying 2 times the array x. So when you do that, it multiplies 2 component-wise to each element of x. Whereas if you allow me to go up a bit, we had an exercise here where we are multiplying 2 to an x where x is a list. And when you do that, it does something which is quite non-intuitive. It simply appends the list to itself, because see, multiplication as an operator has to be defined. So for lists which can store elements of different types, multiplication would the most general way to have multiplication is you just have that multiple times. Whereas for arrays where you have all the elements of the same type, the multiplication operator works differently. Similarly, the addition operators also will work differently. So this is highlighted in the next cell where you have component-wise operation. So you can have an array, and then you can take a square root of the array. So square root will again run component-wise. It will take the square root of each element of x and so on. So you can have as many different operations as you want. They'll all be working component-wise. So here in the last cell that we have here, it allows us to learn about indexing. So we have defined A here as an array which is multidimensional. So you can see that we started with a list of lists. So 1, 3 is the first list and 2, 5 is the second list. And you combine them into one list and you convert that to an array. So when you do that, what happens is it makes the array as multidimensional. In the sense it becomes a matrix, where 1, 3 becomes the first row and 2, 5 becomes the second row. So you have 2 rows and 2 columns in this case. And then you can index them. So for example, I want to index into the first, so in Python, all the indexes start from 0. So 0, 0 is the first row, first column element. So if I do 1, 0, it basically means the row number 2 and column number 1. Okay, so row number 2, column number 1 is element 2. So if I try to print this element 1, 0, so that will give me 2.0, which is the first column and second row element. Similarly, if you want to print the whole row, then you simply give the row number, and then instead of giving the column number, you give a colon. Colon means everything. So then it will print the complete row 1, 3. Okay, similarly, you can have the entire column. So rather than giving the row number, you simply give colon and then column number 1, which is basically the second column. So which gives 3, 5. But in this case, 3, 5 is given as a list or an array is returned. So you have 3, 5 here. Okay. Is that clear? Any questions? So exercise 3 is on linear algebra. Again, extremely important for us in this course, where we will be working with matrices and vectors. So this exercise is helping you learn how to solve the linear system Ax equal to B. And that is also typically what we do in CFD. Okay, so this is extremely relevant. So here what we do is we define a 2 by 2 matrix A, and then we define a vector B containing 2 numbers. Okay, so it's a 2 by 2 system. And then when we, the first exercise is what happens if you write A times B or A star B. Star means multiplication. Now remember, A and B are both arrays this time. So now we'll work with arrays, not lists. So have a look at what happens when you do A multiplied by B. And then in item 4, it talks about using the dot function. So you will see that the star function, the multiplication, is actually not what we expect when we multiply a matrix to a vector. So for that, what we want is we want a dot function. So when you run them, you will see the difference. And then finally, once we have learned about all these, we will be now calculating the inverse of A to calculate the value of x vector. And the second way is you actually use the solve function available in numpy, which allows you to solve a linear system using Gaussian elimination, or it actually figures out the best way to do the solution, the solving technique for you, and uses that. It uses the most efficient technique that is available. Okay, so learn about all this, and the outcome or the learning outcome is that ultimately we'll be using the solve function, which is the most effective in these situations. So please try exercise 3 for the next 5 minutes. Rather than writing the code yourself, just to be time effective, you can copy and paste the code snippets available in the HTML that I've shared in the codes folder, and understand what is happening in that situation. For practicing writing codes, which I highly recommend, because once you start writing things, it goes in your memory better. You can try that at home. Right, so let's move on. So let me quickly run the exercises here. So the first one is which allows us, well, multiple exercises are solved in the first code cell. So we import numpy as np, and then we define the matrix A as a numpy array, not as a list. So we convert that list, multi-dimensional list, to an array. Then we print the value of A just to make sure that we have got the right matrix. We also define a vector B, which is the vector 1, 2. We print the value of B just to make sure that it's everything is happening as expected. Then we use the star operator to multiply A and B, and then we also use the dot function available in numpy. We call it as np dot dot. So dot is inside numpy module, so we access that, and when calling dot, we pass the matrix first and then the vector. So let's run it and see what we get. Okay, so first we see the matrix A, which is 1, 3, 2, 5, and then the vector B 1, 2. And when we do multiplication of A times B, what we get is a matrix, not a vector. So definitely it's doing something which is unexpected, or not what we intended to do. But when we see the result of the dot function, it is giving us a right thing. So you can see that when you multiply the vector 1, 2, it multiplies 1 by the first column of the matrix, so 1, 2, and then it adds 2 times the second column, which is what you expect in the dot product or matrix times a vector. So we get 7, 12. Whereas for A star B, what it does is it takes the first element of the vector, it multiplies by the first column of the matrix. So that is 1, 2. It takes the second element of the vector and multiplies that by the second column of the matrix. And it gives you that 2 columns separately. So this is in a way component-like operation. You take one element, multiply it by the first column, second element by the second column. But that is not what we intended here. So the idea or the takeaway message here is that we need to use a dot function in when multiplying a matrix by a vector, rather than using a star operator. Now in the next code cell, we see that we import 2 functions. One is the inverse function, and the other is the solve function. They are both available in a submodule called linalg. So in NumPy, which is a collection of numerical libraries, there is a linalg submodule available inside NumPy. So to call linalg, we have to use numpy.linalg, and from linalg, rather than importing everything, it is always recommended you import the functions that you need. So we imported inverse and solve. So first what we do is x1 is simply a dot product of the inverse of A times B. So that will give us the correct solution. And the next one is solving the linear system using the solve function. Both should give us the correct answer. The only difference will be that the second way, the solve function way, will be slightly faster than, or is sometimes much faster than the inverse, calculating the inverse. Inverse calculation is an expensive operation. We don't need to do that, as you already know, in solving a linear system. But here we can't see that difference. But for situations where your matrix is large, you can definitely see the difference in terms of the time. Okay, so the next exercise is for plotting, next few exercises. Exercise 4 is to create 2D plots. So I'll run and show you what I mean. So it generates the sin x function here, 2-dimensional plot. So you can play around with the code, change the function, you can change the intervals, or you can change the size of the domain and so on. Exercise 5 is to draw 3D plots. So here we have a contour of a function of x and y, so a 2-dimensional function. We can also have, if I unselect line number 12 and I run it again, you can also have color bars here. So what we see is that is a color map. Rather than having just the contours for discrete values of the function, you can have a continuous color distribution for it's like having a continuous distribution of contours. So that allows you to visualize things much better. Okay. And the next exercise is for surface plot. So for functions z is a function of x and y, rather than using contours or color maps, you can also use a surface plot. So that gives you an understanding of how the surface z is a function of x and y looks. Okay, so you can practice these, and then because we are tending towards the end of the class, I'm running through the exercises quickly, then you can run these at your own time. So exercise 6 is for infinite series sum. So the first problem, square root, was for sequences. This time you have an infinite series. So we know that from Taylor series, we know that the more number of terms we include, the closer the estimation of the Taylor series is to the exact solution. Of course, infinite terms is what exact representation is. So here it's expected from you to use the infinite series of exponential, and you appreciate that if you add more and more terms to the series, the estimate becomes more accurate. So I'll just run it and show. In fact, we are plotting the result here as well. So the orange one here is the exponential that you calculate, and you can see that it is tending towards the exact solution as it gets flatter. So as you add more and more terms, the incremental benefit you get is much smaller. So you have to stop at some number of terms and say that, okay, 7 or 8 terms is enough for me. Because numerically, if you have an infinite series, you have to trim it at some point and then use it as a solution estimate. And the error, which is the difference between what you have calculated using this infinite series or a finite trimming of the series and the exact solution from numpy, the error is also plotted here as a blue line. You can see that blue is tending towards 0. So blue is simply the orange minus the exact solution. Exercise 7 is to give you an understanding of Python functions. So what happens is, if you are defining your own functions, rather than working in your own complete big code, you can define functions and call them again and again. So if you have repetitive work happening in the code, define that repetitive work into one function and then call the function rather than using that snippet everywhere again and again in the main code. So here we are showing you how to use, how to define a function for exponential that you have just done in the previous exercise number 6. And finally, exercise 8, which is for finite differences, the forward difference, backward difference, and center difference. This exercise expects you to estimate the derivative using these 3 methods and compare that to the exact derivative. Because in this case, the function that I have given you, you can easily calculate the derivative of the function exactly. So you can take a difference between what you have estimated and what the exact value is of the derivative, and you can see the error. And in fact, we see the truncation error changing with delta x. Because remember, forward difference and backward difference are order 1 scheme, whereas center difference is second order. That is, the error in center difference goes as delta x squared. So as I decrease delta x, I will see the error in center difference falling much quickly. Okay, so let's run it and see the result. So here the result, what we are plotting is, for the 2 schemes, center difference and forward difference, we are plotting the error versus delta x. Delta x is h here. So you can see that as I decrease my delta x, this is a log scale, the error goes down much quickly in the center difference method. And that is shown by the slope. So if something is some constant times delta x squared, if you take the log of that, you get 2 times log of delta x. So if you have an exponential variation, if you take the log, the exponent can be seen as a slope of the curve. Okay. So what I mean to say here is that actually you'll have y equals some constant times delta x squared, because it's not exactly equal to delta x squared. You'll have some variation, some constants. If you take the log of both sides, you get 2 log x plus log of k. Okay, so you can then see the slope of so if you're plotting log y with log x, the slope of the curve of this log curve will give you the exponent of delta x here. Well, actually this has to be delta x. So let's call it h. And this y is nothing but the error. So by the way, this Jupyter notebook also helps us to write LaTeX, use LaTeX here as well. So it's much easier if I'm representing things. So if error is k times h squared, then if you take the log of both sides, then log error becomes some intercept plus the slope times log of h. Okay. And typically this will be the pace of labs that we will be having in this course. So what is expected? So I don't expect you to understand everything in the lab 100%. So the way you can maximize your understanding in the lab is if you read about the lab beforehand. So please go through the questions and try to solve it yourself before coming to the lab. You can discuss with each other. The more you discuss with each other, the better you will learn. So peer-to-peer learning is more effective than one-to-many learning in this case. Okay, so please, and especially when writing codes, the more you discuss, the better you'll understand. So please do that, and then during the lab, I'll explain the ideas to you. You may not understand them, or you may not be able to do it yourself until you try it yourself. So try running things in the lab and seeing the solution, and after the lab, please try to write the code yourself, either looking at the code line by line or trying to write it without even looking at it. So once you're able to write it yourself, that is the final step in learning. Sometimes we can see the result, a solution, it makes sense, but when you try to write it yourself, it all goes blank. And that is what happens in programming. So I'll test programming through assignments and a course project, which is worth a total of 25% in this course. So it's significant. So these labs are not irrelevant. Even during the exams, I'll test some ideas that you learn through programming in the lab. I may not ask you to write the code, but these subtle ideas you'll only understand if you have run things or written the code yourself. Because this is a very applied course, CFD. There's not much to learn if you can not write the code or you cannot understand writing the code yourself. Okay, so we'll stop the lab now. You can leave if you want. If you want to practice things here, I'll stay for some more time with the TA. You can ask us questions. Any questions that you have?
Why is the dollar sign used here?
That is for LaTeX. So in this markdown, just to separate a normal text from LaTeX, I use a dollar sign. So you can see that whatever was between the dollar sign has a slightly different font and it interprets that differently. So when I was using delta x, that delta slash delta could be converted to a delta symbol. That is in LaTeX. So LaTeX, if you don't know about it, it's worth learning about it. It actually helps a lot nowadays when you're writing technical documents. If you want to write an equation, it's very intimidating. How do you write an equation? You open equation editor and so on. Here you can keep writing things continuously, and when you compile it, it will interpret that itself as a LaTeX code. Jupyter Notebook allows you to combine almost everything, including text, LaTeX, code, and images and so on into one document.